All right. Hey everybody. Welcome to lesson 2B, graphs. All right. So this one's a pretty fun one. There should be a lot of review for you, but if there isn't, pay close attention. We're going to go over the basics of graphs and then talk about the relationship to functions. So, like I said, basics. At the end of this, you should be able to identify points on the Cartesian plane. You should be able to read the coordinates of a point on the Cartesian plane. You should be able to recognize what we mean by the four quadrants. And if I tell you what a quadrant is, I want you to know which quadrant I'm talking about. You should be able to explain the difference between a function and a graph. You should be able to use the vertical line test, and you should be able to use the graph of a function to solve the function. Remember when we said solve a function, that's when we say at what point x is the function equal to 4, that kind of thing. So we're going to use graphs to do those. Graphs are actually the easiest way to display information where it's easy to solve. And so for that reason, they get used quite a bit. They're wonderful, but you got to get through the basics. Graphs. So let's begin. Super basics, the Cartesian plane. That name is super weird. It's named after Descartes, the French philosopher who said, "I think, therefore I am." Yeah. So the Cartesian plane's this. It's a simple system composed of two lines or more. This is a two-dimensional Cartesian plane. You can go to 8 dimensions if you want. So there's a line. We call this the x-axis. And there's another line. We call this the y-axis. And these lines are marked. So 1, 2, 3, 1, 2, and then on the left-hand side and below, they're marked with negative numbers, counting out. -1, -2, -3, -1, -2. Okay, so let's talk about the anatomy of this. This point here, where the lines meet, that's called the origin. Okay, and the origin is it's the point. It's an important point, but it's just the center of a graph. It's the point with respect to which all other points are described. Okay, so when we talk about the origin, we're talking about where the axes meet here, the origin. Okay. Now, the purpose of the Cartesian plane is it allows us to label. Oh, give me a pen here. Label. It gives us an unambiguous way of talking about different points in two-dimensional space, right? So you can say, here's a point. That's point A. This is a different point than, say, this point down here. Call that B, which is a different point than this point over here, C, which is a different point than this point over here, D. Okay. So the point to the Cartesian plane isn't just that it lets us label different points. I mean, A, B, C, D, that's fine. Giving points names is fine. But the Cartesian plane allows us to assign numbers to each of these points, which describes their relationship to each other. Okay? In other words, we're giving these points numbers, and those numbers are like an address. So somebody tells you they live on the intersection of 3rd Street and 5th Avenue. You can find that address on a map by looking at where they meet up. The same thing here. You need two numbers to describe where you're at, essentially. These are called the x and the y coordinate. Or as a pair, they're called a coordinate. These are the coordinates of a point. And what they are is they're two numbers corresponding. If you draw a vertical line down and if you draw a horizontal line across, they correspond to the numbers here and here. So this point A is located at the point x equals 3 and y equals 1. Does that make sense? That said, right. So let's try another one. This one here, you draw a vertical line. It's at x equals 2, and a horizontal line, y is equal to -1. You might be familiar with the board game Battleship, where you give 2 coordinates corresponding to every point. I think the battleship is at A3. I would like to fire a torpedo at A7, right? Where you give 2 different coordinates corresponding to every point on the grid. The idea here is the same. That said, writing your coordinates in this way is fairly space... what's the word? It takes up a lot of space. Hold on a second. All right, just making sure my audio's on. It takes up a lot of space, and so we have a shorthand for it. And that shorthand corresponds to writing a pair of parentheses and a comma, and you write 2 numbers in here. The first number is the x-coordinate, 3, and the second number is the y-coordinate, 1. Okay? So in this case, in point B, the coordinate is 2 minus 1. So let me clear some stuff up here. I'm going to make this easier to read, and we're going to do some exercises. Oh, it's the people. Hey, how's it going?
Okay, how are you today? I'm sorry, I just want to clean a little bit. So if you need it, if you don't need it, okay, I will start that.
Yeah, I don't think we need it this week.
Okay,
thank you. Have a nice day. The custodians come and clean our offices on the weekend. Well, they don't. They make sure that there aren't any apple cores on the carpet and stuff. Yeah, no, they're lovely people. Okay, so where were we? Right. Let's write the coordinates for each of these points. Point A. Oh, give me a pen here, please. Point A has coordinates. Point B has coordinates. Point C has coordinates, and point D has coordinates. Like I said, 2 numbers with parentheses around them, separated by a comma. The x-coordinate, the x value, is always the first, and the y value is always second. Let's go for each of these. So point A, like I said, it's at 3 and 1. Its x-coordinate is 3, its y-coordinate is 1. Or you can think of it as +3, +1. Point B, its x-coordinate, you draw a vertical line, its x-coordinate is 2, its y-coordinate is -1. 2, -1. Okay. What about point C? You draw a vertical line, its x-coordinate is at -1, its y-coordinate is at +1. -1, +1. And, oops. And then D, draw a vertical line, its x-coordinate is -2, its y-coordinate is -2. All right, before we go any further, why don't you take the same diagram and try these, E and F. If they are at point 1, 2, and at point -3, 2. Try to locate these 2 points on the graph. Where are the points? Try drawing them on your own piece of paper. So to locate a point, that x, that tells you that it's somewhere along this line. So let me get rid of this brown one. Okay. And the y-coordinate, that tells you that it's somewhere along this line. Just like if you're talking about where the location is on a street. All right, so if we gave you the coordinates of a point in a city and we said it's the intersection of 2nd Street and 3rd Avenue, you would draw a line along 2nd Street and you draw a line along this avenue and you're at the intersection of the point. Okay. So that's point E. What about point F? -3, so that's somewhere along this line, +2, that's somewhere along this line. So it's right here. F. So that's basics for Cartesian, describing coordinates on Cartesian on the Cartesian plane. If you're having trouble with this, I recommend that we talk some more, because this is a fairly basic exercise. It's super important though that you understand how to do it. Important descriptors of Cartesian plane. Okay. There's the x-axis, there's the y-axis. Okay, 1, 2, 3, minus 1, minus 2, minus 3, 1, no, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. Okay. So there are some basic properties of the Cartesian plane, and it's worth talking about. And the first one, it's by properties I mean, how do you put it? They are just basic reference guides that people use. So when people talk about something, when they're describing where something is on the Cartesian plane, it's helpful for you to be able to recognize them on sight. So the first one is the origin. Okay. The origin is the point 0, 0. So that's right there. Okay. There's something called the x-axis. You know what? I'm going to use different colors for each of these. There is something called the x-axis. Oh, geez, I can't write today. And the x-axis is the line y is equal to 0. Okay? And by that we mean that it's this street here. Now, y is equal to 0 everywhere along the street. And we're describing not a single point, but a whole line of points. So you only give one of the two coordinates. Okay? In the same vein, there's something called the y-axis. It's the line of increasing y. And it's the line x is equal to 0. We're not talking about a point, we're talking about a whole collection of points, a whole line of points, and it's this one. And you see that what all the coordinates along this line have in common is that their x-coordinate is all equal 0. Okay? Beyond this, we describe the Cartesian plane as divided into four quadrants. Okay? And the quadrants are written as follows, often in Roman numerals. This is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. By quadrant, we mean we cut up the area into 4. So, the deal here is that each of the quadrants have something in common. All of the points inside this quadrant have something in common. What's that commonality? Well, if you're in the first quadrant, if you're in this quadrant, if you look at your coordinates, so the coordinates of this point are 4, 3. The coordinates of this point are 1, 1. Both the coordinates in this quadrant are positive. The x-coordinate is positive and the y-coordinate is positive. Let's move to the next quadrant. You know what? Let's move to this quadrant here. Okay. In this quadrant, all of the points inside this quadrant have something in common as well, which is that this one, oh, okay, sure, that's minus 1.5 minus 1.5. This one over here is minus 4 minus 4. Both the x and the y coordinates of all the points in this quadrant are negative. The x coordinate's going to be less than 0, and the y coordinate's going to be less than 0. All right, the other two quadrants are slightly trickier. In this quadrant, all of the different points, all the coordinates of all the points in this quadrant have something in common. Let's talk about those. This one here is minus 2 plus 1. This one over here is minus 2 plus 3. Because we're on the left-hand side of the x-axis, all of the x-coordinates in this region are going to be negative. But because we're above the x-axis, all of the y-coordinates are going to be positive. So in this region, the x-coordinate is going to be less than 0. The y-coordinate is going to be bigger than 0. And last, this quadrant, a similar story. We're below the x-axis, so we're in the negative part of the y-axis. So the y-coordinates are going to be negative. Y-coordinates are going to be negative. But we're on the right-hand side of the x-axis, in the part where the x-coordinates are positive. So in this region, the x-coordinates are bigger than 0. Quadrants don't show up as descriptors all that much, but sometimes when we're talking about which region a certain point is, we might say, oh, that's in the second quadrant, not the fourth quadrant, or that's in the third quadrant, right? So it's a descriptor that we use, like talking about north, south, east, west. You divide the Cartesian plane in quadrants, and that helps us describe where points are. It doesn't get used very often, but it is a helpful thing to understand because it does come up once in a while. All right, so let's talk about functions, because in the previous section we talked about functions in a bunch of different ways. So for instance, you could write a table of functions. So a table of functions, you'd have values of x and values of f of x. So x could be 1 or 2 or 3 or 4, and the value, the output for 2, 0, minus 2. That's a Bonny function. And we also talked about it in terms of graphs, right? Where this line here was the x-axis, and this line here, so the horizontal line is x, the vertical line represents the output value. And so you go, well, at 1, this has value, hold on, let me set my axes. All right, 1, 2, 3, 4, 5, minus 1, minus 2. Okay, so to graph this function, to represent this table, this function as a graph, what you'd say is when x is equal to 1, y is equal to 4. So there's a dot there. When x is equal to 2, the output of the function is 2. When x is equal to 3, the output of the function is 0. When x is equal to 4, the output of the function is minus 2. Okay? And so you use these points to represent all the information on the graph, and we talked about how to look up the value of a function on a, on a graph. So the question here is, we've essentially got two types of things, and they're kind of related to each other. One of them is the Cartesian plane. Ooh, that's not working. And the other is a graph of a function. What's the relationship between the two? Like visually they're identical. There's an x-axis, there's a vertical line, there are numbers. What's the relationship between the two? It's worth spelling out that there definitely is a relationship between the two, and we'll talk about that now. The output of this function, graphically, has been overlaid on the Cartesian plane. In other words, we're putting this on an x, y coordinate plane, okay? And so each of these points representing the solution of the function are at coordinate locations. There's a coordinate location for each of these. The x-coordinate of this location is 1, and the y-coordinate is 4. The x-coordinate of this location is 2, and the y-coordinate is 2, right? The x-coordinate of that location is 4, and the y-coordinate is minus 2. Does that make sense to you? Okay. So, when I'm graphing something, I'm placing the solution on the Cartesian plane. Wait, sorry, I'm putting the function graphing the function as a line on the Cartesian plane. So when you do it, the function is represented by a bunch of points, or a line. All of the points on the line will have an x-coordinate and a y-coordinate. The x-coordinate will correspond to the value of the input for some specific point, and the y-coordinate will correspond to the value of the function. And so sometimes when I draw a function on the Cartesian plane, all I do is I say the y value is equal to this function. Okay. So that's the relationship between describing a function in terms of a line and essentially talking about lines on Cartesian planes. Okay, I'm going to say this whole thing in a different way that might make a little bit more sense, starting from the beginning. If I am given a function f of x, so x is the input and the f of x represents the output value, I can plot means represent with a line or some dots the function, which means represent the function on Cartesian plane. So I can plot the function by setting x, the x-coordinate, to equal the input, and the y-coordinate correspond being f of x, the output corresponding to this input. So a shorthand for this is just us writing y is equal to f of x, and that means draw the function as a line on the Cartesian plane. It's kind of an abstract idea here. The idea is, though, all we're saying here is, instead of representing the function as a table, or representing the function as an equation, or representing the function as an arrow diagram, turn those into a function represented graphically. That's what all of this means. Okay? So for example, f of x is equal to x squared is a function. I can't spell today. Saying y is equal to x squared is the graph of a function. It's a representation of the function as a line on the Cartesian plane. Incidentally, let's plot this. How do you plot a function? We're going to get into some advanced function plotting techniques in the future, but one way to do it is just to consider all of the x and f of x values. Okay. So I've been given the function here, and I can just use this algebraic expression to figure out pairs of inputs and outputs. Minus 3, minus 2, minus 1, 0, 1, 2, 3. When x is equal to minus 3, the output is minus 3 squared, so it's 9. When x is equal to minus 2, the output is minus 2 all squared, which is 4. When x is equal to minus 1, the output is minus 1 all squared, which is 1. When x is equal to 0, it's 0 squared, which is 0. 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay? So, if I want to graph this function, what I might do is draw my x and y coordinates. Okay, so this is the x-axis, and this is the y-axis. Okay, let me label them. -1, -2, -3, 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So how do I go from this into drawing this? It's actually a little bit easier than you might suspect. This table represents what the algebraic expression of the function is at a selection of points, right? There are other points in between that I could evaluate it at. Like I didn't evaluate this function at x equals 1.4, and it didn't, right, it's just a collection of it. So these points aren't the function, they're just a representation of some of the outputs for this function, okay? But now that I've made a table, I can think of this as the x-coordinate and this as the y-coordinate. And what I end up with is a collection of points. -3 plus, so -3, and 9 is over here. And so that's my first point. -2 plus 4. -2 is along here, plus 4 is along here, so the next point is there. -1, 1, so it's right here. 0, 0 is right here. 1, 1 is here. 2, 2 is 2, 4 is here. 3, 9 is over here. And like I said, these points aren't the function itself. They're just some of the inputs and outputs for the function. And so if I were to make more points and more points and more points, I might get a collection of points that look like this between each of these. And if you did it again, you'd get more between each of these, and you do it again and again and again, and you just figure out a whole bunch of points, and in the end you'll end up with a line that looks something like this. So we say that this is the line y is equal to f of x, or y is equal to x squared. This line represents the relationship between input x and output of the function. Okay. So just like before, if somebody were to ask me, hey, what is if x is equal to 2.5, what's the output for that? And you can use this graph. 2.5 is around there, and you can say, oh, okay, the answer here is something around, I don't know, 6.6. So you can now use this graph to look up the relationship between inputs and outputs, just like we talked in the last video. Okay, so in other words, when somebody gives us a function like this or a function like this, we can just think of these points in the tables corresponding to x-coordinates and these points corresponding to the equivalent y-coordinates, and then we can represent the function as a line, right? So that's the connection between the two. Asking a student to do it is kind of fun. Asking a computer to do it is super fun. So let's move on. Next question is every line on the Cartesian plane a function? Oh, before we go on, you might be feeling like, oh, hey, will you be asking us to graph things like this? Maybe as one exercise it's helpful. It's not all that useful in general, because at this point in the game, the only way you guys can go about plotting things is just making big tables and then drawing these points on the graph, which doesn't lead to very elegant graphs, and it takes a long time. So at this point in the game, I probably won't be giving you expressions like that and asking you to plot them as functions. That's not an exercise I'm interested in asking you about right now, but it's in the next lesson. I think we go into it. Sorry, not the next lesson. Like lesson, I think 3.C. I teach you start graphing things. So it's not something super important right now, but the overall thing I want you to get out of this is that, yeah, there is a relationship between the inputs and outputs of the function and these points we're trying to graph. Essentially, yeah, the idea is that when we make a graph, we're just taking our function table and pairing off according to input and output, and saying that this input and this output correspond to a coordinate on this function. If you can understand that, we're gold. So the next question, which is actually a related one to the previous one, is every line you can draw in the Cartesian plane a function? Because often they are. So what would make a function, what would make it a function, what would make it not a function? There's the y-axis, there's the x-axis, there's the y-axis, there's the x-axis. Okay, so how about that? So there's a line. One question is, could this line be the graph of a function? Here's another one. Okay. All right. What we have here, sorry, it might be a little bit confusing. I just want two things to point at so I can compare and contrast them. Both of these lines, both of these purple lines are functions. Or rather, they can be representations of functions. I want you to remember our previous discussion about what makes a function a function. A function is just a relationship between some input x and some output. Maybe I should write with a better pen. A function is just a relationship between an input and some output. Okay? And there was very few conditions on what made a function a function. In fact, there was only one condition, and that condition was that the answer couldn't be ambiguous. For one value of x, you weren't allowed to have more than one output f of x. Okay? So as we mentioned before, the way to look up an answer on a function is just to choose that input, x is equal to 3 or something like that, and then the y coordinate at that point, you just draw a vertical line, and then where that vertical line intercepts our purple line, that height here, the y coordinate, is the output. Okay. So both of these, both the lines on the left and the lines on the right can function in this way. 5.5, and the output is, I don't know, whoops. What is that? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Output is 5. Both these lines can function that way. What about this one? This one has a gap in the line. So like, okay, so over here we could definitely go, okay, so when x is equal to 1, 2, 3, 4, 5, 6, y is equal to 1, 2, 3, 4, 5, right? So when the input is equal to 6, the output here is equal to 5. This line can totally work as a function in that way. But what about this part? What about the break? Are you allowed to have a break? You're totally allowed to have a break in the line. Do you remember us talking about domains and ranges? In this case, The range is any value of x that the function is above or below. So any value of x that will work as an input. So when x is less than -1, there's totally an output, right? So for any of these points, you can look at it. All right, there you go. For any value of x bigger than 2, you can use this as a function. For the inputs between -1 and -2, so the inputs in between here, the values of x in between these, it doesn't work as a function. So the domain of the function is x less than -1 and x bigger than 2. Okay. So yeah, both of these will work as a function. So is it true that every possible line can work as a function? The sad answer is no. Let's talk about that. So let's look at this guy as a function. Okay, is this a function? Well, the answer could be yes for some values, like that one. 1, 2, 3, 4, 5, 6, 7. X is equal to 7. Y is equal to, what is that, 4? So yeah, it looks like for this point, you can use it as a function. What about a point over here? X equals 1. You do your vertical line or you draw your vertical line. This line meets the vertical line meets the red line at 2 locations, up here and down here. So the answer could be 1, 2, 3.5, or the answer might be -2.5. Remember that the thing that made a function was that you weren't allowed to have 2 outputs for any one input. Are 2 outputs. So the answer is ambiguous. The output is ambiguous. So it's not a function. So the thing that makes a function is if function is a function. A line is only a function only if there's only one value y for any specific value x. Does that make sense? So asking whether a function is a function if you're given a table, whether or not you can use a particular table as a function, that's kind of complicated because you have to look for repeated elements. Looking to see if there is a super easy way to tell if a graph is a function. It's called the vertical line test, and it's based on essentially the way we've been whoops, let me change that. Evaluating functions at specific points. So the idea here is that if it's a function, you're only allowed one output for every input. Okay, so oh, fine, whatever. And okay. The vertical line test goes like this. Imagine we've got a vertical line. Hello. Cool. Oh, that's not vertical. Let's try again. And I'll maybe a different color here. I'll use green. Okay. Oh, come on. This one. Okay. What we're going to do is we're going to take our vertical line and we're going to sweep it down the x-axis. You're going to take our vertical line and sweep it down the x-axis. The rule here is there might be places where the vertical line doesn't touch the red line at all. That's fine. But the vertical line test, what we're doing is we're asking ourselves, does the line cross the red line at more than one place? It might do it there, but I think we talked about what the open circles and the closed circles mean. If it's an open circle, it means the function isn't defined at that point. So that's actually okay. So this one passes the vertical line test. It doesn't hit the red line at any two places. It's only one place at a time for any of these horizontal things. This vertical line test, oh, in this region, it crosses the red line in 3 places, which is definitely more than one. Okay? So this one passes the vertical line test. And this one fails the vertical line test. If it passes, it can be a function. Or it can be used as a function. If it fails, the line is not a function. Okay? So it's not the case that every line is a function. Some lines on the Cartesian plane don't work as functions. And our test for it is the vertical line test. We just sweep a line horizontally across it. It's a pretty fun test to do, and it's definitely testable. So I will put this on tests and stuff. Okay, so there's a last point I wanted to make about solving functions. Remember, let's say we had a function 3x plus 2. I might ask you, okay, so usually how this works is I give you the value x, 3, and then you evaluate the function at that point. 3 times 3 plus 2 is 9 and 11. Okay? Solving involves doing this backwards. I tell you the value that I want it to be. I want this to be 8, and I'm asking you what value x makes it 8, right? And so this is a linear expression. You would solve this particular one by setting this equal to 8, and then algebraically rearranging it. Subtract 2 by both sides, divide both sides by 3, x equals 2, and then testing it. 3 times 2 plus 2 is equal to 6 plus 2 is equal to 8. Hooray! Okay. We saw solving for quadratics as well. So if somebody asked you to solve a quadratic, you'd complete the square, or maybe you'd rearrange things and use the quadratic formula, right? But that's the issue. We're specifying what the output is, and we're asking you what the input is. Okay, so that's solving equations. That's when we tell you what the output is. Solving for functions, we tell you what the output is, and we ask you to tell us what the input is. And solving functions algebraically is actually fairly difficult. I expect you to be able to do it for linear functions and quadratic functions, but higher order polynomials are a no. Can we solve things if the function is given as a graph? And the answer is yes. I mentioned in the introduction that this is actually the easiest way to solve something. It's easier to solve this, and sometimes you can use graphs to solve functions for outputs without actually knowing -1, -2, -1, -2. You can solve functions without actually, in cases where you couldn't actually do it for algebraically, right? So we can use this technique even if you can't use it algebraically. Functions actually lend themselves quite well to solving. Okay, so this line, y is equal to f of x, it satisfies the vertical line test. Do you want to give the vertical line test to it? Sure, let's give it the vertical line test. Take a vertical line. Oh, geez, I messed it up. Draw yourself a vertical line. And drag that vertical line across the thing. Scan it. See if it crosses our line in more than one place. Nope, it only ever crosses in one spot. Okay. So yeah, it's definitely a function. So somebody gives us a function, and they ask us to solve it. They say, hey, for what value of x is the output equal to 4? How do we do that? It's actually super easy, because what we're looking for is points on the line where the y coordinate is equal to 4. So all you have to do there is draw a line along y is equal to 4 and see where the function intersects it. And you go, oh, right there. The answer is x is equal to 3. There, you solved it. And you can do it for other ones too. Let's try another one. F of x is equal to 2. You just draw a line across x equals 2. There you go. And you go, oh, it's y is equal to 2 when x is equal to 2. You just look at where they intersect and draw a vertical line down to see where it intersects with the axis. So, for instance, roots are great. Roots are when the line is equal to 0. So where is y equal to 0? You just draw a horizontal line across it, and you just read off the points. It's equal to 0 when x is equal to -3, x is equal to -1, and x is equal to +1. Are you allowed to have more than one solution? Yeah, you are. We saw in the quadratic formula that quadratic expressions always have 2 solutions. A thing can still be a function even if if there's more than one value of x that make the same value of y. It's when that order is switched that you're not allowed to do things. In other words, if there was something called the horizontal line test, this particular graph wouldn't pass it, but there's no such thing as a horizontal line test. It's not a thing. So, in other words, we can use these graphs to solve these expressions. It's pretty fun. All right, so let's review. All of this was just kind of an idea where we were talking about the Cartesian plane. The Cartesian plane has axes. There's the x-axis and the y-axis, and they intersect at a place called the origin. We use the axes to describe the location of every point in terms of coordinates. And we're describing a function. What we're doing is we say a function is a particular relationship between the two coordinates, where the x-coordinate is the input of the function and the y-coordinate is the output. And that gives us a line. And also there's quadrants. We didn't talk much about quadrants. You use them descriptively when you're plotting things. But yeah, that's overall it. Thank you for watching this video. Good luck. Talk to you later.